So till whatever portions we complete in module 3 will be the portion for Cat 1 as well. So till Thursday's class, whatever we complete will be the portion for module 3. Okay. So in module 3, we'll take up a little bit more practical problems, more practical situations related to heat transfer, especially conduction heat transfer. So until now, we have seen only one-dimensional heat transfer. So heat transfer in Cartesian coordinates, either heat transferred in x direction or y direction or z direction. Similarly, in the spherical coordinates or cylindrical coordinates, we consider heat transfer only in the radial direction. Some situations uh, are amenable for one-dimensional heat transfer treatment, but there are several other situations where you actually have to go for a two-dimensional heat transfer. So in such a case, you must know the concepts of a two-dimensional heat transfer. Now, if you observe the heat conduction equation, in the heat conduction equation on the left-hand side, you have three terms, three diffusion terms. Let us take the Cartesian equation, one diffusion term in the x direction, one in the y direction, one in the z direction. Then if there is heat generation, you will have this q dot term. And if there is a transient nature of conduction, then you will have this heat accumulation term on the right-hand side. Now let us, for the moment, let us keep the heat generation and the transient term aside. So we are left with three terms on the left side, one in the x direction, one in the y direction, and one in the z direction. Out of which we remove the z direction, then it becomes a two-dimensional problem. So when we solved one-dimensional problem, so we removed y term and z term also. Only x term was retained. Now we are retaining x and y terms, so we are removing the z terms. That means we are not considering a three-dimensional problem, we are considering a two-dimensional problem. Now dou square t by dou x square plus dou square t by dou y square is equal to 0. That will be the nature of equation. Now you can see that each of this term is a second order term. Therefore, you need two boundary conditions in the x direction and two boundary conditions in the y direction. So in this way, the solution becomes a little bit complicated. Okay, so we will see what are the solution methods available for two-dimensional heat transfer problems. As far as the one-dimensional heat transfer problems are concerned, we solve them using what is known as the analytical method. We started with the differential equation dou square t by dou x square. And we said that since the temperature is varying only with respect to x, dou square t by dou x square can be rewritten as a d square t by dx square. That is equal to 0, then integrate it twice, you will get two constants of integration. The values of those two constants of integrations can be evaluated using two boundary conditions. So in that way, you can find the temperature distribution. Once you have the temperature distribution, you differentiate the temperature distribution with respect to x to find the temperature gradient and use the temperature gradient in the Fourier law of heat conduction to calculate the heat transfer. So like any other problem, finding out the temperature at a certain location and finding out the heat transfer and heat flux will be the general questions of any heat transfer problem. So likewise, we have taken up one-dimensional problem in the previous module and solved them. And the method we have adopted is analytical method. So we could solve them, the equations, the differential equations using variable separable methods. Unfortunately, all the equations that we dealt with were ordinary differential equations. Now, since we are going into two-dimensional problems, we are venturing into two-dimensional heat transfer, it means, by definition, it means that the temperature is changing with respect to x and with respect to y direction also. Therefore, the dependent variable is t and the independent variables are x and y. Therefore, definitely we have to treat this as a partial differential equation. And you know, from your mathematics background, you can understand that solving a partial differential equation is a little bit complicated compared to the ordinary differential equation. So we will see what are the different methods available to us in this 2D method. So the next module is called conduction. Conduction part 2, module 3, conduction part 2. Okay. Now, we will deal with the steady state conduction only. Later on, we will go for the transient conduction aspects. We'll first deal with the 2D steady state conduction. So many real life heat transfer problems are two-dimensional. So treating them as one-dimensional will lead to errors. So treating them as 1D will be actually grossly approximating the problem, and therefore you may not get the correct amount of heat transfer, and you may not be able to get the correct temperature distribution. Hence, multidimensional effects must be included. And you can see that the multidimensional effects, if you include, the solution will be difficult compared to 1D. Why? Because in one-dimensional steady state problems, the equations that we deal with are ordinary differential equations, whereas in two-dimensional steady state, the equations are partial differential equations. Now you can see here in this particular figure, what is shown in this figure is a rectangular plate. You see, this is a rectangular plate. The origin is fixed on the left bottom corner, and X is towards the right, and Y is upwards. So this is a rectangular plate, and you can see that this rectangular plate is subjected to different temperatures on its boundaries. Now you see this theta. Theta is usually in a heat transfer. We non-dimensionalize the temperature. So as of now, you don't worry about what is that non-dimensionalizing with the temperature. Just see there is this theta. Theta is equal to 0. Theta is equal to 0. Theta is equal to 0. And theta is equal to 1. That means three sides of this particular rectangular plate are subjected to the same temperatures, and one side is subjected to a different temperature. So what is happening here is you will see that there is a temperature distribution. There will be a temperature distribution, and there will also be certain heat flux. You can see this arrows, these lines indicating arrows. These are called as heat flow lines or heat flux lines. Okay, so they indicate the direction of heat transfer. So theta is equal to 1 is greater than theta is equal to 0. Therefore, heat transfer takes place from high temperature to low temperature. So heat transfer takes place in this direction. So these are the heat flux lines or the heat flow lines, and you can see these are these curved lines here marked as a 0.75, 0.5, 0.25, and theta is equal to 0.1. These are the isothermal lines. Okay, so in this way you can draw what is called as the flux plot. So after solving a two-dimensional problem, this is the kind of a pictorial representation you can come up with. What does this pictorial representation show? It shows the temperature distribution in the entire area, and also it will show the heat flux lines or the heat transfer lines in the entire region. So this is very much similar to what you have seen in fluid mechanics. In fluid mechanics, you came across what is called as the streamlines, right? You know what are the streamlines, and the streamlines are similar to this heat flux lines. Okay, so these lines with arrow are called as the heat flux lines, and these curved lines are called as the isothermal lines. That means the lines joining the points of the same temperature. So you can see it, or you can understand on this side the temperature is highest, and this side the temperature is lowest. So the temperature gradually keeps on decreasing. So theta is equal to 1. So it decreases to 0.75, then 0.5, 0.25, 0.1, and finally theta is equal to 0. So this is the kind of a temperature distribution. Now you can see that the temperature distribution is changing with respect to x direction, also with respect to y direction. Therefore, this becomes a two-dimensional problem. What are the methods of solution available for the two-dimensional problem? There are three generally available methods, but only one is practically used. We will see the first one, which is the analytical solution. So analytical solution means using the concepts of mathematics, especially solution of the partial differential equations, and framing the equation and the boundary conditions for the problem of interest currently that we are dealing with, and using that equation, that partial differential equation with the boundary conditions, we solve it. We solve it analytically. So you use the concepts of calculus and solve that. So that is one method. The problem with that method is it's mathematically involved, and limited problems only can be solved. yields accurate results at any point. So the advantage of this analytical solution is that it is a continuous solution. It gives accurate results at every point. So if there are infinite number of points in a domain, then you will be able to solve this equation at infinite points. So you get accurate results at any point. But problem is it is mathematically complicated. You cannot solve any problem. If you have a complex shape, you will not be able to uh, solve it using concepts of mathematics and calculus. That sometimes it is, most of the times it is impossible. The next option is a graphical solution. So this is one of the solutions that was used before the advent of the computers. So using the graphical solution, which we shall see in this class, using the graphical solution, we can get some approximate answers. So using that approximate solution, we will be able to determine or able to have an idea of how the temperature distribution will be there and what will be the temperature at a particular location in a given domain. But it has got certain disadvantages. Firstly, it needs a skill. It's a time consuming method. The person using must be skillful, and finally, even with all that, it gives only approximate solution. But the advantage is that before you go into trying to solve, obtain an analytical solution or the next one, the numerical solution, this graphical solution will give you a good idea of how the temperature distribution would look like in the domain. So that's the advantage. The last one and the most popular one is called as the numerical solution. You have seen mathematical methods in Maths 1, Maths 2, or your calculus and so on. And you must be now convinced that it's some of the methods are quite difficult. There are a lot of theorems involved and so on and so forth. Now, as pointed out in the first analytical solutions, not every problem can be solved analytically using mathematics. Therefore, we resort to numerical solutions. What happens to numerical solution is that we reduce whatever equation is there. We try to reduce that equation to simple equations involving Boolean algebra. So simple equations involving plus, minus, multiplication, and division. And then we will end up with a number of equations, number of simultaneous equations to be solved. If there are 100 unknowns, there will be 100 equations. We will have to solve them. But on paper, 100 unknowns, 100 equations is extremely difficult to solve, but it is very easy to solve using a computer. So if you can program that particular problem and using the numerical solutions, if you can frame the equations, it's very easy to solve it. So if you are good at programming, then numerical solutions are one of the easiest way to get a reasonably good solution. So all the softwares that you see, the computational fluid dynamics software, FEM softwares, and so on, ANSYS, Fluent, and so on, they take up this numerical solution method. So what they do is they break up the region, the domain, into a number of small volumes, small control volumes, and apply the governing equation to those control volumes, and of course with the boundary conditions, and come up with a number of equations. So if your domain is very large, then you will have a large number of equations, sometimes millions of equations. Those millions of equations will have millions of unknowns, and they all have to be solved simultaneously. Manually, it is impossible, but you will have to use a programming method to solve them. Therefore, these solutions can be solved easily using a program, but it will take time. Even for a high-speed computer, it will take some time, depending on the problem. It could even take few weeks to arrive at a solution. So just for the sake of demonstration, I have showed you an analytical solution. You take a two-dimensional problem, a rectangular plate having three sides maintained at a temperature 0 and one side maintained at a temperature 1. So just to be practical, let us say these three sides are 0 degrees Celsius and this side is 100 degrees Celsius. Okay, when you non-dimensionalize them, you will get 0, 0, 0, and 1. How you will see, don't bother about it now. So the governing equation is dou square t by dou x square plus dou square t by dou y square is equal to 0. How did we get this? By removing the z term on the left side and the heat generation term on the left side and the transient term on the right side of the conduction equation. We got this. Now temperature is T. We can non-dimensionalize it using this formula, T minus T1 by T2 minus T1. You will get a non-dimensional form. Don't worry much about this. So this equation is now transformed into this equation. Dou square theta by dou x square plus dou square theta by dou y square is equal to 0. And the boundary conditions are at x is equal to 0 and any value of y, theta is equal to 0. So x is equal to 0 and any value of y, theta is equal to 0. Similarly, at x is equal to at any x and y is equal to 0, you have theta is equal to 0. Similarly, at x is equal to L, so at this side and any y, theta is equal to 0. And at this phase, at at any x and y is a value of w, theta is equal to 1. So in this way, we can this conditions we can represent mathematically using this equation. To take a close look later on. Now, using the variable separable method, people have solved this equation, and this is the solution. So temperature theta at any location x and y can be obtained using this. Now you can see here the solution involves an infinite summation. N is equal to 1 to infinity. That means you cannot practically go from 1 to infinity. You will have to stop somewhere. That means even after so much of effort, so much of mathematical brilliance involved in obtaining this, when you try to compute it, you will have to stop. Let us say maybe at n is equal to 10 or n is equal to 50 or n is equal to 100, you will have to stop because you cannot go on until n is equal to infinity. Then you see there is a sine trigonometric functions, sine function, hyperbolic sine function, and so on. So because of this, the analytical solution obtaining itself is difficult, and after obtaining it, you see you still have some approximations to make. So this is the problem involved with analytical solution. But if you are able to solve it, then it will be good and it will be valid, and also you will have an intellectual satisfaction in obtaining this analytical solution. But that is not always possible. Therefore, we have another option called as the graphical solution. So as I said, graphical solution is an old method, but it makes sense and it gives a physical interpretation or physical understanding of the system that you are trying to solve. So in graphical methods are suitable only for 2D problems. So these are not suitable for 1D problems. These are not suitable for 3D problems, but only 2D problems. And also there's another limitation. You see, only isothermal and adiabatic boundary conditions are possible. So that means only two conditions, isothermal and adiabatic. Isothermal means constant temperature and adiabatic means insulated boundary condition. Only these two boundary conditions can be evaluated. So you can see that the first 2 points are pointing out at the limitations of the graphical solution. But later on, this method is superseded by computers. It's taken over, but presently it's used to obtain the first estimate of the temperature distribution. So before we actually venture into the computers or analytical solution, it's always practical, or it's always good to have this graphical solution. So how this graphical solution is? The underlying principle is that the lines of constant temperature must be perpendicular to the lines of heat flow. So we are talking about two different lines. What are they? Lines of constant temperature. That means the isothermal lines must be perpendicular to the lines of heat flow. Lines of heat flow means heat flux lines. So heat flow lines and constant isothermal lines must be perpendicular to each other at any point wherever they cross. The first step is to construct a plot of isotherms and heat flow lines. So this is keeping in mind that the isothermal lines must be perpendicular to the heat flow lines. We should first plot what is called as the flux plot. This flux plot is used to infer the temperature distribution and heat transfer. So how does this look like? Now you see here, before going into this, let me this image. Now you see here, you see these are the heat flow lines and these are the isothermal lines. Now the condition is that the isothermal line and heat flow lines must be perpendicular to each other. So this angle must be 90. This angle must be 90 degrees. So this so this way, this also. This way, each one of these must be perpendicular to the other. In that way, you should be able to draw. You will get a correct. So here you see there is this domain. We'll understand this domain. This is looks like a trapezoidal domain. Two lines are parallel, and these two are parallel lines. Looks like a trapezoidal section, and the this side is maintained at a temperature T1, and this side is maintained at a temperature T2, and the T2 is less than T1. So T1 is greater than T2, therefore heat transfers from left to right. Okay. Now you see this representation means that this is adiabatic. So this is adiabatic. So this is adiabatic. This also is adiabatic. So remember, for using the graphical solution, adiabatic and isothermal conditions of boundary conditions only are allowed. Nothing else is allowed. So that is there in this particular problem. So we have two boundary conditions having adiabatic conditions and two boundary conditions having isothermal conditions. So this entire side is at temperature T1 and this entire side is at temperature T2. So we can attempt to solve this problem using the graphical solution. So what we do is we construct the flux plot. We know that T1 is greater than T2. So we draw the heat flow lines from this point to this point. So something like. And to this heat flow, perpendicular to this heat flow lines, we should draw this adiabatic lines. So something like this. In such a way that this heat flow lines and adiabatic lines are perpendicular to each other. So this angle, this region is shown here. This is the heat flux line and this is the angle. This is the isotherm, this is the heat flux, and this is right angle. So this condition has to be satisfied whenever you construct this flux plot. And remember, flux plots are manually drawn plots. So this you must keep in. So what are the different solutions, different steps involved in the graph plot is identify all the relevant lines of symmetry. So line of symmetry, whenever you have line of symmetry, that line of symmetry acts as a adiabatic condition. So line of symmetry are heat flow lines and hence are adiabatic. Sketch the lines of constant temperature, which are isotherms. So isotherms must be perpendicular to the adiabatic. So first identify the symmetries. Symmetries will tell you where things are adiabatic. That means where heat flow is zero. And then draw the constant temperature lines. And based on that, you should make sure that the isotherms, the constant temperature lines, are perpendicular to the adiabats. So heat flow lines or adiabats must be drawn to obtain the network of curvilinear curves. So curvilinear squares. So you will have some network of squares which I will show you. All sides of each square must be of the same length. So for this problem that we have seen here, if we draw or for this problem, see this let us say we'll take the example of this rectangular plate with a square hole or a square plate with a square hole at the bottom. So you see at the center. So you see here, these are the regions available, and you can see these are the lines of symmetry. There are symmetricity along the diagonals, along the two diagonals, and there is symmetricity along this line and this line. So identifying all the lines of symmetry, you will see that there are 8 segments here. 8 segments are formed. Now, among the 8 segments, you choose any one segment. In this figure, this segment is chosen. So choosing this segment, is sufficient, and you don't have to work out with the all other 8 segments. That means in this, by choosing this segment, by choosing one segment, you are actually reducing the burden of work. So you see this segment is is symmetric to this segment. This segment is symmetric to this segment. This one to this one to this, and so on. So this is a representative of the entire thing. So you do the evaluation for this region and then multiply with 8. So there are 8 such things now. So multiply with 8, that will give you the final result. So like that you have to do. So you see here, you take this segment and represent it here. So this segment is shown here in a larger image. And you see here, this is a line of symmetry. So this line of symmetry is the adiabatic line. Is adiabatic. So here the heat flux is 0. Similarly, this line is this line. So this is another line of symmetry, though this acts as an adiabatic. And also by the basic definition of this plate, the inner face is maintained at temperature T1 and outer face is maintained at a temperature T2. So this side is T1 and this side is T2. So you see here we have two sides having constant temperatures and two sides having adiabatic condition. Therefore, we can attempt this problem and solve it using the concept of graphical solution. So what we do is the temperature T1 and temperature T2. So heat flux must be from this point to, okay. So we draw this, let us assume T1 is greater than T2. So heat goes from T1 to T2, and these are the heat flux. These are the heat flux lines, and these are the isothermal lines. So the vertical lines that you see are the isothermal lines, and the horizontal lines are slightly inclined lines. These are the heat flux lines. And you can see once we construct this diagram, you see here heat flows lanes, and these are the isothermals. So you'll have to draw in such a way that you maintain this right angle. It takes some effort. In fact, it takes a lot of effort to do that, and it will not be, you will not be successful doing it in the first attempt itself. So once you complete this kind of a flux plot, you will end up with with a network of squares. So in this figure, this particular square is taken and shown here. To this square, there is a heat entering in the left direction, heat entering in the right direction, and also on the top you have one flux line, and on the bottom you have other flux line. That means these flux lines basically are adiabatic lines. Therefore, there won't be any heat transfer on the either side. Therefore, you see this representation as adiabatic. So heat flow is taking place here in this particular direction, and you can see here this particular square. Let's call this as a square, even though the sides are a little bit curvy. This side is delta x, and this side is delta y. Now delta x is represented as a AB plus CD by 2. Okay. So AB plus CD by 2. These two are not exactly identical. Therefore, we are taking an average of this. That will be the dimension of the side in the x direction. Similarly, in the y direction, AC plus BD divided by 2. So this will be the average dimension of this particular square in the y direction. Why do we need this is to later we'll have to calculate the thermal gradients and also the areas. Now you can see here how to estimate the heat transfer rate from this. So the same figure I have shown once again so that we don't have to go back and forth. So the total heat transferred will be equal to sum of the heat transferred in each of these lanes. So here in this square, Qi is flowing. So Qi is the same heat that is entering this lane, passing through each of the square and going out. So Qi is entering here, it is passing through this square, and it is also going out. Qi is the same. So in this lane, heat transfer is Qi. Similarly, in this lane, there will be a different amount of heat transfer. In this one, there will be different amount of heat transfer. So the total amount of heat transfer will be sum of the heat transfers in this one, this one, this one, this one. That will be Q is equal to uh, sum of sigma Qi. I is equal to 1 to m. So This is represented as m multiplied by qi, where m is the number of lanes. These are. So here you see in this particular figure, 1, 2, 3, 4, 5. There are 5 lanes here. So in general, we have represented as m. M multiplied by qi. So qi is the heat transfer in each lane, and m is the mass, the number of lanes. So that is how it is represented. Then qi is kai dot tj by del tj by del x. So if you try to evaluate qi in this one, if you apply the heat transfer conduction equation for this law of heat conduction, then heat transfer is Ka delta T by delta X. I have dropped minus signs to avoid complications. So this delta T will take care of this positive temperature difference. Okay. So this heat transfer is K is the thermal conductivity of this material multiplied by the area across which this heat is flowing, multiplied by delta T. That means temperature difference between this point and this point. So this is delta Tj divided by delta X. So delta X is the distance through which this heat has to travel. So delta T by delta X will give you the thermal gradient. Now K is left as it is. Area for heat transfer is delta Y multiplied by L. So this is delta Y. This side is delta Y, which is AC plus BD by 2. So this delta Y multiplied by L is the length of this plate. That length of this plate is into the slide. Delta Y into L multiplied by this term thermal gradient. Now delta T1 to 2. Now you see here delta T1 to 2. So this entire overall temperature difference, delta T1 to delta T1 minus T2, that's delta 1 to 2 is equal to sigma j is equal to 1 to n delta Tj. So if you break up this temperature differences into small gradients, into small see, this is T1 and this is T2. If you break it into these small segments, the total temperature difference will be sum of each of these temperature different segments. We do that breakup, and delta T1 2 is equal to sigma j is equal to 1 to n delta Tj. So we are actually adding the temperature gradients in each of the segments and summing up from 1 to n. That becomes n multiplied by delta Tj. So n is equal to total number of temperature increments. In this particular thing, you can see 1, 2, 3, 4, 5, 6. So these are the temperature increments. So the number of lanes are 1, 2, 3, 4, 5. 5 lanes and 6 temperature increments. So n is the total number of temperature increments. Now you see that if you assume that delta x is equal to delta y, if you draw these squares in such a way that delta x is equal to delta y, that means deliberately make them square, then this entire thing will you substitute delta Tj, in place of delta Tj, you substitute delta 1 to 2 divided by n, and this one, we will see that Q becomes, so this thing with Q becomes mln multiplied by K delta T1 to 2. That means delta T1 to 2 is the overall temperature difference, K is the conductivity, M is the number of lanes available for heat transfer, N is the number of thermal increments, and L is the length of the object. So this L is the geometric property here. So the entire problem has been reduced to finding out the number of lanes, number of thermal increments, and then we can easily solve it. So by constructing this flux plot, we can find out what is the value of M and. So this is how a general flux plot is evolved. It doesn't start. It doesn't come up in the first attempt. You will have to do a lot of trial and errors. So what you have to do here is, here you see there is this geometry, two sides of the geometry. This side and this side are adiabatic. This face and this face are at a temperature T1, and this face and this face are at a temperature T2. So what you have to do is draw the heat transfer lines. That means from T1 to T2, let us say T1 is greater than T2 or T2 is greater than T1, whichever is, that doesn't matter. You keep drawing lines from T1 to T2. That will be the heat flow lines. Then you will have to draw the adiabatic lines in such a way that this perpendicularity is maintained. So you will have to first draw a trial one, then erase some lines and draw the final one and so on. So ultimately, with a lot of trial and error and repetitions, you will get this kind of a flux plot. So these are the, yes.
So why is the fifth line on the top side slightly bent like an S shape?
Which one?
So the last line, that one, which is where your cursor is now, somewhat
Okay,
of an
this one.
S shape.
Oh, this is slightly yes, sir. Oh, no, this is also like yes, right? It's not straight. This is also yes. This looks straight. Okay,
Yes,
this
sir. So
also
like,
looks
how
like
do we
yes.
know whether we need to go S shape or more straight line?
To maintain this perpendicularity. Okay. If you
Okay.
go straight, you may not be able to get this perpendicularity. So you to maintain this perpendicularity, you will have to go in a S shape. And if you draw more and more lines, see this is only partially drawn, but if you draw something like this, you will see that at this point it should take a slight curve so as to be become an S shape. Okay, so that's why this method is needs skill to do. Okay, but ultimately, if this is done, if the flux plot is done, the thing will become more easier. For example, you can count. Now, what you can do is you can simply count the number of lanes here. You see here, 1, 2, 3, 4, 5, 6 lanes. Now, if I take only one half, the asymmetry, I can take only this half, and provided these two are of the same side, but unfortunately, this side is not same as this side. So I will have to take the entire thing. So I will count number of lines, flux lanes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. M is equal to 12. Then N is equal to how many temperature gradients am I breaking this into? This side is T1, this side is T2. Oh, 1, 2, 3, 4. N is equal to 4. So in this way, I will be able to estimate the values of M and L, M and N. Then L will be given, and the K will be the material property, and the temperature difference. This T1 minus T2. This temperature difference will be involved in finding out that. So after doing all this, people have come up with what is called as the conduction shape factor. What is this conduction shape factor? So finding analytical solution for solution for 2D and 3D conduction problems is difficult. Therefore, rapid solutions to some problems may be obtained using existing solutions obtained from analytical as well as a graphical methods. So these solutions are reported in the terms of a shape factor. So for easy or quick reference, these standard shapes have been pre-solved and made available in the form of tables, and a new term called as the conduction shape factor is introduced. Now remember, this is a conduction shape factor. You will also come across another shape factor called radiation shape factor in the radiation heat transfer. So just make sure that these two, you understand that these two are different. So the shape factor S is a dimensional conduction heat rate, and it is defined as a Q is equal to SK delta T. Okay. So this is how the shape factor is defined. Heat transfer is equal to shape factor multiplied by conductivity multiplied by the overall temperature difference. Now, how to evaluate this shape factor? Now, by definition, this is it. And from the graphical method, you see, this is the equation that we have derived. This is the definition of the shape factor, and this is the equation from the graphical method. So if K and delta T are common, so you can say S is equal to ML by N. So S is equal to ML by N is the way in which we can evaluate the conduction shape. So using this concept, people have come up with the tabulated shape factors. So here you see there are several geometries. For example, the first one is isothermal sphere burned in a semi-infinite medium. So don't bother about this word semi-infinite medium now. So there is a sphere burnt underground, and for this the shape factor is given like this. How did they come up with this? They used graphical method or analytical method to evaluate the heat transfer, and then they compared that equation with this equation and evaluated what is the value of S. Factor has been obtained. Likewise, here there is a horizontal isothermal cylinder and vertical cylinder in a different configuration. Then here conduction between two cylinders of length L in an infinite medium. So if you bury two cylinders in some medium, what will be the interaction between them? What will be the heat transfer between them? So something like that we can also find out. So these are the tabulated shape factors. Now these shape factors, not all of them that you see in the screen, but some shape factors are already given to you in page number 61 of your data book. Okay, so you can refer to the data book, page number 61 as well as 62. 61. So these two pages. So now using this, we can actually solve some problems. We'll take up a simple problem and see how to solve this using these concepts. Now, a hole of diameter 0.25 meters is drilled through the center of a solid block of a square cross section with 1 meter on each side. The hole is drilled along the length L is equal to 2 meters of the block, which has a thermal conductivity of K is equal to 150. A warm fluid passing through the hole maintains an inner surface temperature of T1 75 degrees Celsius, while the outer surface of the block is kept at T2 25 degrees Celsius. Using the flux plot method, determine the shape factor of the system. Also estimate the rate of heat transfer through the block. So this is the problem. So basically what we have here is a square object, what's the name called? Square, a solid block of square cross section. So there is a solid block of square cross section. There is this hole, a through hole of the same length as that of the solid block is drawn. This center, the inside surface temperature is maintained at 75 degrees. Outside temperature is maintained at 25 degrees Celsius. The material conductivity is given as 150 watt per meter Kelvin. This side is W is 1 meter and the other side is also 1 meter. So it's a square cross section. So in this, we are asked to find out, determine the shape factor of the system. Also estimate the rate of heat transfer through the block. Okay, so shape factor can be found out using using this formula ML by N. So you can see here. Firstly, to solve this, the flux plot has to be constructed. So that has been already done, and you see that these are the lines of symmetry. One line, second line, and also there are diagonal lines of symmetry. So after all that, you get one common region, this region, which is symmetric to other regions. So we evaluate this region. So in this region, which is shown here, so this face is shown here and this face is shown here. So this surface is at T1, this surface is at T2. So this is used to construct the flux plot. So T1 is given as 75, T2 as 25. Therefore, heat transfer has to take place in this direction. So you draw this heat flux lines here, and perpendicular to the heat flux lines, you draw the adiabatic lines here. So we know that this is a line of symmetry, so this is adiabatic, and this also is a line of symmetry. This is adiabatic. So you join these adiabatic surfaces using these lines so that they are perpendicular to the heat flux lines. So make sure that these are perpendicular. So if you do that, you can see that we come up with a flux plot. Now you can see that there are how many lanes in this particular diagram. The number of lanes are M is equal to 1, 2, and 3. So M is equal to 3, number of lanes of heat transfer. Similarly, how many temperature increments? So from T1 to T2, how many parts did we break into that difference? So T1 is 75, T2 is 25, so difference is 50. That 50 difference is broken into 1, 2, 3, 4, 5, 6. So we have N is equal to 6. Okay. So what is L? We also have the value of L. L is 2 meters. Therefore, the shape factor is S is equal to ML is equal to M is 3, L is 2, by N is 6. So this is the shape factor, but this is the shape factor for one but there are 8 such segments. So total shape factor is 1 multiplied by 8 is equal to 8. So that's the shape factor for this particular geometry. Now this we obtained using this flux plot. Remember, this creating the flux plot is a kind of an art. It comes with experience, and different persons will be able to draw it differently. So here there are only three heat flow lanes, but somebody may come up with 5 heat flow lanes. For them, M may be different, and also N may be different. So ultimately, this S is equal to 8, whatever we got, is an approximate value. Remember, this is not analytically obtained, this is approximately obtained. But you see this we have you see this case 6. In case 6, you see circular cylinder of length L centered in a square solid of equal length. So this is a square solid and this is a circular cylinder of length L. So in such a situation, this situation is similar to the one, the inside surface is T1, outside surface is T2. In such a case, the shape factor is made available to us through this equation. So we'll try to find out what's the shape factor from tables. S is equal to 2 pi L divided by logarithm of 0.08 W by W is the width and D is the diameter. So this you can evaluate 2 pi multiplied by L is equal to 2, and natural logarithm of 1.08 multiplied by width is 1 divided by D is 0.2. So evaluate this, you will get it as a 8.58. Okay. Now this 8.58 is different from 8. What we had here is 8, but the actual analytical value is 8.58. But you see here 8.58 is very close to the rough estimate 8. So this flux plot method can be used for initial estimate. But the accurate value is 8.58. So units is meters. So we'll use this to calculate the value of Q. Q is equal to S K delta T, isn't it? K delta T. You have the formula here in the data book also. So you is 8.58 multiplied by K is 1 multiplied by delta T is 75 minus 25. So this should give you the answer we have here, 64 kilowatts. 64 kilowatts. So if you use 8 in place of 8.58, you will get a slightly different answer. But since now we know that 8.58 is the correct one, that's what I used to find out the heat transfer. It is 64 kilowatts. Okay, so this is one way of easily solving a two-dimensional problem, provided we have only isothermal and adiabatic boundary conditions. Okay, so this is one way of solving a two-dimensional problem. Tomorrow I will take up another problem also, this problem, and we'll go for other methods later tomorrow. So tomorrow we'll continue with this. I think I'll stop here and continue. Take your attendance. There's some message. Somebody posted a message. Vito has got some electricity problems. All right. Let me take your attendance. Rutunidhi? Rutunidhi?
Present, sir.
Present, sir.
And Cherian?
Present, sir.
Now Dilip,
Present, sir.
Present, sir.
Watson,
Present, sir.
Ken,
Present, sir.
Palanivel,
Present, sir.
Yes, sir.
Ranjan,
Present, sir.
Sir,
Vaibhav Karan,
Trishant, present, sir.
Present, sir.
Vaibhav Karan,
Present, sir.
Abhijit Menon,
Present, sir.
Sri Krishna, Adil Sinju,
Yes, sir. Present, sir.
Turvedi,
Present, sir. Present, sir.
Hassan, Ayush Tripathi,
Present, sir. Sir.
Vardhan,
Present, sir.
Present, sir.
Molly Singh,
Present, sir.
Sai Rohit,
Present, sir.
Sir, Subhania present.
Sri Raman,
Present, sir.
Tal, Ish,
Present, sir.
Sudh
Yes.
Venkat,
Yes, sir.
Sri Kumar,
Present, sir.
Krishna,
Present, sir.
Present, sir.
Inti,
Present, sir.
Present, sir. Present, sir.
Narayanan, Badri Narayanan, Avito,
Present, sir.
Ajit,
Ajit present, sir.
Harsh Raghav, Harish
Present,
Raghav,
sir.
Present, sir. Rahul.
Firoz,
Present, sir.
Nihar,
Present, sir.
Karthik,
Present, sir.
Gauri Shankar,
Present, sir.
Modi, sir. Present, sir.
Yes, sir.
Pooja,
Present, sir.
Prem Kumar,
Yes, sir.
Ran Sarvesh,
Present, sir.
Ran Ajay, Paul Simon,
Present, sir.
Ish,
Present, sir.
Yanakshaya, Dev,
Present, sir. Present, sir.
Kunal Rao,
Kunal present, sir.
Ish Krishna,
Yes, sir.
Vedant Madhur,
Present, sir.
Anand,
Present, sir.
Shivani, Priya Vasan,
Present, sir.
Rai Priyan,
Present, sir.
Narayanan,
Present, sir.
Manish present, sir.
Kush Raj,
Present, sir.
Keshav Kumar,
Present, sir.
Karthik Prasanna,
Present, sir.
Tab, Varun Halyan,
Present, sir. Present, sorry, sir. Present, sir. Sai
Present, sir. Varun.
Kaustubh, present.
Varun Halyan,
Present, sir.
Sarvesh Krishnan,
Present, sir.
LC Femina,
Present, sir.
Effort GNL,
Present, sir.
Manoj,
Present, sir.
again Madhusudan,
Present, sir.
Palanivel, Trishant,
Present, sir.
Yes, sir.
who is that? Palanivel,
Sir, Pioneer present, sir.
Krishna, Praveen,
Praveen present, sir.
Hassan,
Present, sir. Hamza is present.
Hemant Kumar,
Heyman present, sir.
Sir,
present.
Yes, sir. Present.
Vishal,
Present, sir.
Badri Narayanan. Charan Ajay. Vamsi Krishna. Jnanakshaya.
Present, sir.
Jnanakshaya.
Sir, Vamsi Krishna present.
Vamsi Krishna present, sir.
Varun. Shivani.
Present, sir.
Akash Kumar.
Present, sir.
Sai Kausab.
Present, sir.
We'll meet tomorrow. I'll.
Sir, Vishal present, sir.
Vishal, what's your number?
19 BME 1152.
Not you present.
Oh, okay, sir. I was
Yeah,
facing mic issues, so I didn't know whether
I present whatever I mark here, so you should be able to see that. Okay.
yes, sir.
You can leave
Thank
the
you.
class now. We'll meet tomorrow again.
Thank you, sir.
Thank you, sir.